Okay, the next section is dealing with similarity. Much like 6.3 was dealing with angle-angle, we're pulling back side-side-side and side-angle-side similarity. Now, if you remember, in Chapter 4, we dealt with the congruencies of side-side-side and side-angle-side, and now we're dealing with side-angle-side, side-side-side similarity. And again, that idea of similarity, similar, means proportional. The whole goal in Chapter 4 of proving triangles congruent was proving corresponding parts congruent. This chapter we're dealing with similarity. Proving triangles similar is accomplished by proving corresponding parts similar or proportional. Once you've proved corresponding parts proportional, then you've proved the triangles were proportional. If you look at this first theorem dealing with side-side-side similarity, it's saying that if corresponding parts, like AB and RS, reduce to the same fraction as, say, BC and ST, and the same fraction as, say, AC and RT, then the two triangles are similar. But you'll notice that they had to prove all three sides to be the exact same ratio before they could say the triangles were similar. This is the exact same method as finding scale factor, by the way, which we did in the very first section of this chapter. So what they want us to do is, in this first example, is prove, are any of these three triangles similar? What we're going to do is we're going to set up ratios comparing corresponding sides in all three. Now this gets difficult when you've got triangles that are various sizes and in various positions. I'll tell you the easiest way to do it is by going through and solving for the longest side, or establishing the longest side. The longest side of this is ln. The longest side of the second triangle is TS. The longest side of this third triangle is XY. Now the reason we do this is the longest sides should be proportional to each other, the shortest sides should be proportional to each other, and the middle sides should also be proportional to each other. So what we're going to do is we're going to establish our ratio by setting up fractions using the longest sides. What I'm going to do is I'm going to compare ln to TS, which gives me 26 over 33. Whoops, except when my computer messes up like that. 26 over 33. Then I'm going to set up the exact same thing in between these two, dealing with TS and YX. 33 over 39. And then last but not least, I'm going to use the outside ones, ln and XY, but I'm going to set it up over here, just so I keep all three, scattered out. 39 over 26. Now, if any of these will reduce, that's what we need to do first. We need to try and reduce them. 26 is actually a very odd number. We don't deal with it a lot. The only two numbers that go into it are 1, 2, 13, and 26. 33, on the other hand, 1 and 3 will go into, but that's and 11. But we don't get any common factors here. 26 over 33 actually will not reduce. 33 over 39, however, 3 goes into both. 3 goes into 33 11 times. 3 goes into 39 13 times. And so we get the reduced ratio of 11 over 13. Then when we go over to 39 over 26, we're in the exact same boat. And actually we're not, sorry. 13 will go into both. I apologize. 39, 13 goes into 3 times. 26, 13 goes into twice. So we have a ratio that won't reduce, a ratio that will reduce, and a ratio that does reduce. Then let's grab the shortest sides of all three. Let's find the smallest side of this triangle, which is 20, the smallest side of this one, which is 24, and the smallest side of this one, which is 30. Then what we're going to do is set up the same idea, the ratio of this triangle to that one, dealing with the smallest sides, 20 over 24. Then the ratio of these two, 24 over 30. And the ratio of this triangle with the last one, which gives us 30 over 20. Now what I want to do is try and reduce these, but you should start to notice that the ratio should end up being the same as the first ratios we found. Meaning the ratio of the smallest sides and the ratio of the longest sides, if the triangles are similar, they should be the same. Here we get 20 over 24, which reduces to at least 10 over 12, which already is different. Now 10 over 12 will reduce again to 5 over 6, but we still don't have the same. So we've already proven that these two triangles cannot be similar by side, side, side. The reason they can't be similar is because at least two of the sides need to be proportional. We just proved that two sides are not proportional. In fact, really none of the sides are proportional. Well, then we go to the next two. 24 over 30 should reduce to 11 over 13. The smallest sides should be the same ratio as the longest sides. 24 over 30, I know that 6 goes into both. 6 goes into 24 4 times. 6 goes into 35 times. You'll notice that I have two different ratios here. Okay? Which means that these two triangles cannot be similar by side, side, side. Now, I'm not even going to take into effect their angle measures. I'm just being told, or I'm just asking, are they similar by side, side, side? So far, we have two sides that are not the same ratio in both. Now, the last possibility is this last triangle being similar with the first triangle, or the first with the last. So, I need to reduce 30 over 20. Now, it's fortunate that both of these 10 will go into. 10 will go into 33 times, 10 will go into 22 times. You'll notice that I have two ratios that are the exact same. And now what I'm going to do, since I've already compared the longest, I've already compared the shortest, I'm going to actually go back and grab the third sides, 24 and 36. Now, in each of the previous two, I dealt with the longest side on top. I dealt with the bigger triangle first. So I'm going to do the same thing, 36 over 24. I know that 12 goes into 36 and 24, so I'm going to use 12 as the reduce. 36 divided by 12 is 3. 24 divided by 12 is 2. And if you notice, I get all three sides of this triangle and this triangle to reduce to 3 over 2, which means that the triangle is indeed similar by side, side, side. Now, notice it says, if so, write a similarity statement. I have to be able to go through, and I'm going to erase all this junk, get it out of the way, so to speak. Now I'm going to go through and prove or write that this triangle, L, M, N, is similar to triangle. And you got to be very careful on how you write these. Notice we went from the highest point clockwise. I need to go to the highest point, which is this one. Notice we didn't start at the base. We started at the highest point. So we're going to start with X, and we're going to go clockwise from there. X, Y, Z. And we've proven that these two triangles are similar by side, side, side. Let's look at the next page. Theorem 6.3 deals with the exact same idea, but this deals with side angle side, meaning you have two sides that are similar, and the included angle, the angle in between the two sides, is congruent. Remember, sides have to be proportional, but in two triangles, the angles have to be congruent in order for the shapes to be similar. So let's take a look at this example number 2. In example 2, it's asking, tell whether xzy and yzx, xzw and yzx are similar by side angle side similarity, meaning we have to be able to prove a side, an included angle, and another side are congruent, or similar, congruent, similar, before we can say that the two triangles indeed are similar. So what I'm going to do is I'm going to break this down into the two triangles they're talking about. XZW is right here, and then YZX is right here. Now what I'm going to do is because these two triangles are not in the same position, I am going to identify some common characteristics. Here's a 90-degree angle, here's a 90-degree angle, which means the side opposite those is what we call the hypotenuse. So I can compare the two hypotenuse. I can compare 20 over 15. Okay. I can also compare the shortest side, 12, which is the shortest side of WXZ or XZW, and 9, which is the shortest side of YZX. Now, 20 over 15 is, if you reduce both by 5, you get 4 over 3. If you reduce 12 over 9 both by 3, you get 4 over 3. You'll notice that this side is proportional to this side, and this side is proportional to this side. And actually, let me use different colors just so you can see. Here's the problem, though. When you just randomly pick sides in a triangle, when we're dealing with side, angle, side, the angle has to be in between the two sides, which means that in between these two sides is this angle, and in between these two sides is this angle. And so I have to be able to prove that this angle and this angle are congruent. Now, in a few months or in a few chapters, you're going to deal with trigonometry. Trigonometry is a part of geometry dealing with sides of a triangle, whereby you use fractions to solve for the angles. It's very complex, it's very deep, but you don't know how to do it yet. So when I randomly just grab sides and expect to use the included angle to prove side angle side similarity, I'm stuck because I don't know the included angle. Now I want you to watch something. Had I taken the angle that I knew first, you'll notice that when we first started identifying common characteristics, we identified a right angle and a right angle. Now, if I prove that those two angles, we'll call them angle YZX is congruent to angle XZW. Now that we proved the angles are congruent, we can take the sides on either side. Get it? Sides on either side? Anyway. The sides on opposite sides are here and here. And we're going to try and set those proportional to here and here. Hopefully that makes sense, that we're taking the angle that we already know, the angle that we're given, and we're setting that up as our starting point. And now I can take the sides that are on the opposite sides, or on the outside of it. Now, just like I did at the beginning where I set the longest side and the shortest side, I'm going to take the two sides that I'm left with. I'm going to take the two sides that I'm left with and use the same idea, the longest side with the longest side, the shortest side with the shortest side. Now you'll notice 16 is the longest side of this triangle, and 12 is the longest side of this triangle. Don't let it throw you that 12 is shared between the two. You'll notice 12 is a part of this triangle and 12 is a part of this triangle. But they are different parts. So I'm going to say 16 over 12. And then I'm going to take the shortest sides in both, which in this case is 12 and 9, and set that up also. Now I'm going to reduce these and see if I have two sides that are similar. 16 over 12, I know that 4 goes into both. 4 goes into 16 4 times, 4 goes into 12 3 times. 12 and 9, I've already reduced this using 3, so I'm going to use it again. 3 goes into 12 4 times, 3 goes into 9 3 times. Notice this. I have two sides that are similar. I have an angle that's congruent. I have side angle side similarity. But you'll notice that when we started this, we just started randomly grabbing sides. You can't do that. You have to make sure that the angle is in between the two sides when you're using side angle side. Let's go to the next page, which there is no next page. So let's take a look at your homework now.